Right, next I'd like to look at lunar eclipses. And in a lunar eclipse, we have still a straight line relationship between the Earth, Moon, and Sun, but the Earth now is between the Moon and the Sun, so that the Moon is in a shadow, and it's entirely within the shadow. So this means that you can see a lunar eclipse from the entire nighttime side of the Earth, if the viewing conditions are favorable. Okay, whereas with a solar eclipse, you can only see it over a narrow region of the Earth's surface. The umbral shadow is only a total blockage of the sun's light over this very small part of the Earth's surface, and the penumbral shadow is a much larger region of partial eclipse. But in the case of a lunar eclipse, the whole moon is covered up by the Earth's shadow from any point here on the surface of the Earth that can view the moon. Okay, of course, you'd have to have a good horizon view. You couldn't have a lot of clouds, but assuming that you could see the moon anyway, you would basically, well, it wouldn't completely disappear, but it would kind of glow an iridescent orange, and we'll talk about why that's true. But let me just remind you, if we look up at the data projector for a second, how these alignments arise. Remember that the moon's orbit, something like a 7-degree angle with respect to the ecliptic plane, which means that most of the time the lunar phases' shadows miss each other. But in a few select points, the moon can cross the plane of the ecliptic when it's on the far side of the Earth from the sun. And so this would be the case then when it is in this configuration or in this configuration on the far side. And so that is the kind of the other end of the configuration from when we'd have a solar eclipse. You'd have a solar eclipse if it were on this side, and a new moon phase as it crosses the plane of the ecliptic. But on the back side, as it's crossing the plane of the ecliptic, if it happens to be in a straight line with the Earth and the moon and the sun, then you can get this lunar eclipse. Now, the duration of a lunar eclipse is about 4 hours. And so the Earth's shadow then is has a width that's equal to the diameter of the Earth. That width is about 8,000 miles. Okay, and so the moon then would be a full moon when it's on this side. Then it would move through and into the shadow. So this would be full. Then it would be eclipsed. And then back to full again. And so this would take about 4 hours to move through the shadow. And so that means that it takes 4 hours for the moon to move about 8,000 miles. So this means then, and the Greeks actually figured this out something like 2,500 years ago. They figured out that the moon must be moving about 2,000 miles an hour. They knew the size of the Earth, and so they knew the width of the Earth's shadow, and they were able to measure and here we're really looking at the maximum duration of a total lunar eclipse, because the moon could move through on a glancing blow through the shadow and only be within the shadow for a shorter period of time. But by looking at the maximum duration for a lunar eclipse, they're able to get the speed of the moon's orbit around the Earth, about 2,000 miles per hour. Once we know the speed of the moon's orbit, and we know that it takes the moon 1 month to go all the way around, you can just say that 1 month in hours. So that would be something like 28 days times 24 hours per day. So this would be the number of hours in a month. So then you could just use rate times time equals 2 pi r, which is where r is the distance from the Earth to the moon. And so the rate then is 2,000 miles per hour times the time, which is 28 times 24 hours. Divide that by 2 pi, and you have the distance from the Earth to the moon. So the Greeks figured this out too. So this turns out to be about 250,000 miles, or as we saw before, about 1.3 light seconds. So this duration of the total eclipse then is an opportunity for you to see the moon go through a complete set of phases, basically from full to new, and then back to full again. And also, by studying the shape of the shadow of the Earth on the moon, the Greeks concluded that the moon was a curved surface, because they knew that it was the Earth's shadow that was blocking the light. And so when it became partially eclipsed, they could see that there was a curve to the shadow of the Earth on the moon. And so that could only occur if the Earth was a curved surface. And so they, at that point, said that there was proof that the Earth is curved, and it probably has the simplest curve shape. It looks, because the sun is a big ball and the moon is a big ball, so the Earth is probably a big ball too, and that was right. And so they were able to get a lot of key pieces of information from the observation of a lunar eclipse. And so that's kind of the history of it. In terms of what you would see today, first we'll look at these basic definitions, and I'm supplying you these PowerPoints too, so you can check in Module 1, and you'll find these under PowerPoint. And so partial lunar eclipse then occurs when the Earth is only partially able to block the light of the sun on the moon. And so here then is the configuration. We see here the light that's coming from the sun. Here's the shadow. Then there's the moon in the shadow. But look at here. The moon is this kind of bright orange. And so it actually, there is something to look at during the lunar eclipse. So you say, well, it's in the shadow. How come it has any kind of light coming off of it at all? It seems like if it's in the shadow, there shouldn't be any light at all. Well, oh, and by the way, here we can see the kind of a time-lapse shot of the moon going around the Earth and then going through the umbral part of the shadows, the part in which total blockage is occurring. But you also have the penumbral shadow where you can get a partial eclipse. And so there we see what the eclipsed moon would look like, kind of this orangish color. And by the way, it turns out that if you want to see a total lunar eclipse, your best bet is to use binoculars and not to use a telescope, because there's not enough light to really resolve well with a telescope. But we have light coming from the sun, okay? And so that light is a combination of all the different colors, from blue to red. But what happens as the light goes through the Earth's atmosphere is that it bends a little bit. And the blue light is taken out because the sky is blue. And so what that means, the fact that the sky is blue, is that blue light is scattered better by the particles of dust, as well as by the nitrogen and oxygen molecules in the Earth's atmosphere. And because it's a different density medium, there's a little bit of bending, just like with eyeglasses, okay, as the light travels through. So the red light then survives traveling through the Earth's atmosphere and bends a little bit due to this lensing effect. And similarly, that's happening on this side too. And on this side, and on all the sides as it's coming in. Okay, so the blue light is gone then. The red light bends a little and illuminates the moon with a little bit of red light. So this makes it kind of interesting to observe. And it gives you something to look at. So it doesn't just disappear. But we do go from the full moon to the kind of orangish, glowing eclipse moon, and then back to the full moon again. And so since this is visible from the entire nighttime side of the Earth, the next time you see it, and you've probably seen a few of these already, just because it is so easy to be in the right position to view one, you might try to look for the point where it's moving through the shadow and see if you can see the curvature of the Earth's shadow, and see if you could deduce what the Greeks were able to deduce, that in fact proves that the surface of the Earth, which is blocking that light, must be a curved surface. Okay, so let's ask a couple of questions about this. First of all, let's ask, what would be a phase of the Earth as viewed from the moon during an event that we would normally view from the Earth? Okay, so let's say that here's the Earth, here's the moon, and here's the sun. Okay, so this would be, we know already, that would be an eclipse of the sun by the moon. But if we viewed from the moon, what would we see? Think about this for a second. If you're looking at what we would call an eclipse of the sun by the moon, but you're looking from the moon point of view. Let's say that we're looking toward the Earth. Can you see here that what we would see would be a full Earth? But with a little dot in the middle, an umbral and a penumbral shadow. So you'd have a full Earth, but you'd have the umbra here and the penumbra around it like that. Okay, and so there'd be kind of a little bullseye here in the center where it would be dark. And then surrounding that, it would be partially dark in the penumbral shadow, and then the rest of the Earth would just be illuminated by the sun. Okay, but what so this would be, from the Earth's point of view, a solar eclipse. But I think it's kind of fun to think about how these things would look from other perspectives. And it also helps us, I think, a little too, to see what's going on. Okay, so during a lunar eclipse from the Earth, well, what would you see from the moon? If you're looking this way, in the direction of the Earth and the Sun. Well, I think that you can see here, since the moon is entirely within the shadow, that means that you can't see the sun at all, right? So that means you'd have a total eclipse of the sun by the Earth. And this would be viewed from the entire nighttime side. Of the, I'm sorry, this would be the entire near side. It would be only nighttime side from the Earth's point of view, but it would be from the entire near side of the moon. And because the Earth is something like 4 times the diameter of the moon, the Earth would look much bigger than the sun from the point of view of the moon. It would look about 4 times bigger in diameter. It would have 4 times the angular size. Because if the moon looks the same size as the sun, and the Earth is 4 times bigger, then this is roughly still the same distance. And so the Earth would look 4 times bigger. So it would cover up more of the solar corona during this total eclipse. And you could see it from the entire near side of the moon that would be viewing them. What if you had a first quarter moon phase? What would you see? What phase of the Earth would you see? During a first quarter lunar phase. Well, we need to draw a picture, of course. And so here's the Earth. Here's the moon going around the Earth. This would be new, that would be full. This would be third or last quarter. This would be first quarter. Assuming that the light is coming in like this from the sun. Coming in as parallel beams. And illuminating this side of the moon and putting that side in the shadow. Okay, so let's think about this for a second. If you're here on the moon, you see a full Earth. If you're on this side during a full moon phase, you'd see a new Earth. So here you are standing here, you're seeing full Earth. Here you're standing here on the moon, you're seeing new Earth, because the side of the Earth that you're looking at is the side that's in the shadow. The sun is only illuminating that half of the Earth that is closest to the sun. And so if this is full and this is new, then this is telling me this is third quarter Earth. And then that tells me this is new Earth, and we're coming around to here, and we're on our way to full Earth. This would be first quarter Earth. and so those kinds of phases then are visible if we're in a rocket ship. Oops. Oh, okay. Quick here, I'll pull this back up. And there. There. That's the picture I wanted. So we can see here this picture was taken by a rocket ship that was on its way to Jupiter, the Galileo space probe. And interestingly, it went to Venus first to get a booster shot of speed. Turned out that the extra distance that it had to travel to go to Venus was more than made up for by doubling its speed, so that it could make it to Jupiter faster by going to Venus first, stealing some energy from Venus and then rocketing at faster speeds to Jupiter. But on its way back, it was able to take this snapshot of the Earth and the Moon together in basically the same phase. Looks like a first quarter phase for both of them, but from a rocket's point of view. And so we can see the difference then in size. So an Earth phase would look much bigger than a lunar phase if we were standing on the Moon and viewing it, because of the differential in size between the Earth and the Moon. Okay, so those are the main things that I wanted to talk about then with respect to eclipses of the Moon. The next thing that I'd like to talk about are constellations. And so why are we interested in constellations? Well, constellations act as a coordinate system that can help us locate objects in the sky. So it's a fixed pattern of stars. And so we choose what patterns we call the constellations, so that we can all agree on which patterns are what. I mean, you could look at this pattern of stars here, and you could say, well, that doesn't really remind me of some hunter clobbering an animal. But several thousand years ago, this did remind the Greeks of Orion the hunter. And that was basically this pattern of stars here. Okay? And so this is seen in the southern sky and is particularly visible in the wintertime. This is a large nebula here, the Orion Nebula. And one thing that we can say about constellations is that although all of these dots look like they're kind of projected onto a two-dimensional screen, they're actually at different distances away. Okay? And so we would see that if we went to a different perspective on the stars by flying away from the Earth. But from our point of view on the Earth, they have this pattern, and it doesn't change much over even tens of thousands of years. Okay, and then here's another set of constellations. Here we have the Big Dipper, and we have the Pointer Stars, which points to the North Star, and that's part of another constellation called the Little Dipper. And then these two stars from the Big Dipper point down to Regulus in the constellation of Leo. And if you follow this curve of the handle, and this is basically going over the whole sky. You know, if you actually want to check this out, you're going to have to arc down to Arcturus, which is in this constellation of Boötes, and then swing on down to Spica, which is in the constellation of Virgo. And so by identifying certain constellations, this can help us to see what's going on with different objects in the nighttime sky. Okay, so that's how they're useful then. And in particular, we're going to see in this section how to locate planets as well. Which is kind of a fun thing to do. Okay, and so these constellation patterns don't change much. Over a human lifespan. And actually what we see is that they do change, though, say over hundreds of thousands to millions of years. So if we were to project what the Big Dipper might look like in a million years, that the stars in that constellation might have changed, say, into a spear or something. So the reason for this is that here we are in the galaxy. We're in the plane of a spiral galaxy. And so as our solar system goes around the galaxy, it goes around at slightly different speed from other stars that are in other parts of the galaxy. Okay, so look here, maybe that star's moving a little faster, this star's moving a little slower, and so the result of all of this then is that what we see in terms of these patterns will very slowly change over time. We're not going to see much of a change in a human lifespan because it takes 250 million years for us to go around once, okay, around the center of the galaxy. Something like 250 million years to go all the way around once. And so these other stars then might have slightly different periods of orbit around the center of the galaxy. And so slowly but surely their orientation with respect to us would change. But we don't have to throw away our star wheels after, say, 20 years. You know, they're still pretty much the same as they were before. And also, the Earth's axis kind of spins like a top. And so this can change the position of the constellations with respect to our coordinate system, because the Earth's axis doesn't always maintain the same orientation. Now with the seasons, we were saying, yeah, it doesn't change much. It goes around to this side, then to that side. It hasn't changed much. But that's over 1 year. If you go, say, 26,000 years, it goes through a complete gyroscopic precession. And so that can also change at least the positions of the constellations over longer periods of time. And so the reason for that is very much the same reason that a gyroscope works. Here, it's the pull of the Earth's gravity that causes the spin axis to change direction. but the torque is being exerted by the sun on the Earth, and that's what's causing this gyroscopic precession of the Earth over these longer time periods. Whereas here, this precession might only be a period of, say, a second or two at the most, whereas in a big gyroscope like the Earth, it could be tens of thousands of years, in that case 26,000 years. So if we are interested then in trying to find out how to make use of this coordinate system, we should be clear then as to what's happening at the center of this coordinate system. It turns out the North Star is at the center of our coordinate system. And so how would we locate the North Star? Well, it's easy. All you have to do is go to the North Pole and look straight up. Nothing to it. Just go to the North Pole and then look straight up overhead, and there will be the North Star, which is called Polaris. Okay, so that's the easiest way to find Polaris if you're already at the North Pole, or if you can get to the North Pole. However, if you're not already at the North Pole, then what you have to do is, okay, so here, to find the North Star, go to the North Pole and look overhead. However, at some other latitude, say where we are, if we don't want to go anywhere, and what's a latitude? Well, latitude is just one of these angular measurements that goes from the equator up to the North Pole. Okay, and so if you were, say, at the 45th parallel, you'd be in southern Montana, and you pass this sign. I did it last summer. It said, "Congratulations, you're halfway to the North Pole." Okay, and so that's kind of a good accomplishment. But it's an angle that's drawn out from the center of the Earth. So 0 degrees north latitude would be right on the equator. But 90 degrees north latitude would be at the North Pole. So this would be 0 degrees, this would be 90 degrees, and say here in San Luis Obispo, let's say we're at 35 degrees north latitude. Okay, so if we're there, and this angle here is 35 degrees, measured from the center of the Earth up to our location, then if we're at some other latitude, for example, 35 degrees north, then you look toward the north. So you look this way, which is toward the north, and then you look up above the horizon at an angle that's equal to your north latitude. Okay, so this angle here then would be 35 degrees. From the horizon view to looking straight toward the North Star then would be looking up above the northern horizon by 35 degrees. Okay, and so if you're at the equator then basically you're looking at the North Star right on the horizon. because you're looking at 0 degrees north latitude. At San Luis Obispo, North Star at about 35 degrees above the horizon. And at the North Pole, as we said before, just looks straight up, or that's 90 degrees north latitude.